So today we are going to talk about power factor correction. Put this out of the way. So in our lecture on Tuesday, we talked a bit about what power factor is, a measure of the efficiency of power transmission in a system. And I had mentioned that sometimes large industrial consumers, like manufacturing plants, often operate at a power factor that is less than 1 due to the presence of numerous inductive loads like electric motors. We also talked about how average power is what the consumer pays for, and apparent power is what the utility pays to produce. And if that ratio of those two quantities is too low, the industrial customer, like a power plant or something, or excuse me, like a manufacturing plant, can face a fine because effectively the electric utility is spending money to generate power that gets sent out to the consumer and then gets sent immediately back, because the reactive power is not capable of performing any work. Okay. So what power factor correction is a process that is used to increase the power factor of a industrial consumer to an acceptable level to meet some threshold, typically somewhere around 95%, 97.5%, or something like that. The expectation isn't that you have to correct the power factor to 1. You just need to bring it up so that the level of inefficiency is smaller. So let's consider a power triangle diagram for a generic inductive load, right? So here we have our real axis, here we have our imaginary axis, and let's say that our load I'm going to call this S old. This represents the complex power absorbed by our load prior to applying power factor correction. And we know that the length of this vector is our apparent power. The projection of this vector onto the real axis is our average power, which I'm going to call P old. The projection of this vector onto the imaginary axis is the reactive power, which I'm going to call Q old. And it forms some angle with the positive real axis, which I'm going to call theta old, right? We know that power factor is simply the ratio of P old to the magnitude of S old, and that is also simply the cosine of the angle theta old. So these are all relationships that we talked about in our last class meeting. So if I want to increase my power factor, make it closer to 1, does that angle theta old need to get larger or smaller? I'm old, so if you said anything, I couldn't hear it. Larger. Larger. So take your calculator out. You guys all have calculators? Do the cosine of 10 degrees and do the cosine of 30 degrees and tell me which one gives me a larger number. 10. So in order to increase our power factor, we actually need to make that angle smaller, right? As that angle gets larger and larger, it gets closer and closer to 90 degrees, and the cosine of 90 degrees is 0. Whereas if that angle gets smaller and smaller, we're looking at the cosine of something close to 0 degrees, and the cosine of 0 degrees is 1. Okay. So we want to make this angle smaller. There are two ways that we can do this. Mathematically, both work. Practically, one is very stupid. So that's what I'm going to talk about first, and then we're going to talk about the way that it's actually done. So I'm going to extend my real axis here really quickly, give myself a little bit of room. You don't need to necessarily write this part down because we're doing the dumb thing that isn't done in practice, but mathematically works first. Okay. So if I were able to make my load absorb more average power while holding my reactive power constant, right? So let's say that I had some, let's do it in this light blue thing here. New average power. My new complex power, S new, would be over here. And let me put my projection like so. And my new angle, theta new, is definitely smaller, right? So causing my load to absorb more average power does increase my power factor, okay? Now let's talk about why that's wildly stupid, right? What do we as consumers pay for? Is it average power or apparent power? Average power. So effectively, we would be running up our utility bill in order to avoid paying a fine, which doesn't make a whole hell of a lot of sense, right? We are paying more money to avoid paying more money. Doesn't work. Mathematically, works great. Practically, it's about the dumbest possible thing that you could do. So if changing the real part of our complex power isn't the answer, then obviously we need to change the imaginary part of our complex power in order to make our power factor better. So I'm going to erase this S new thing because once again, it's really dumb to do it that way, even if mathematically it works. So we want Q to be smaller, right? So if, for example, we had some new Q, like so, while holding our average power to be constant, like this, we get a reduction in our power factor angle, which corresponds to an increase in our power factor, and we haven't changed our utility bill at all, right? Because the amount of average power that is being absorbed or consumed by the user has stayed constant. So this begs the question, how do we lower the reactive power that's absorbed by a load? So let's look at a couple of different things here. Okay. Right. So if we had a resistor, we know, or at least we should know, that in the RMS frequency domain, V is equal to I times Z. And from this, we could say that the complex power absorbed by a resistor is going to be the voltage drop across the resistor times the conjugate of the current flowing through the resistor. This is a relationship that we learned in our last class meeting. So if I substitute in I as V over Z, what we're going to get is V times V over Z conjugate, which is going to look like the magnitude of our voltage squared divided by the conjugate of Z. And for a resistor, our impedance is simply real, right? So this is just going to look like the magnitude of the voltage squared divided by the resistance. So is this a real number or an imaginary number? It's a real number, absolutely right. So since it's a real number, it's not going to have any influence whatsoever on the reactive power, right? It's only going to have an influence on the average power. So putting resistance in our circuit isn't the answer. Right. So here's what it looks like for resistor. If we use an inductor, using the exact same expression, the magnitude of the voltage squared divided by the conjugate of the impedance. I'm going to do something here just really quickly. So 1 over negative J. Let's look at this down here. I'm going to erase this little thing. I'm just showing you a proof here. So 1 over negative J. If we multiply that by J over J, what we get is J over negative J squared. What's negative J squared? Positive 1. So 1 over negative J is the same thing as positive J in the numerator. So this is going to look like J times the magnitude of the voltage divided by omega L. Okay. So is this a real number or an imaginary number? It's an imaginary number. There's a J output, right? Is it positive or negative? Always positive. So that means if we were to add inductance, we would actually make Q larger. So that's not the right answer either. So instead, by process of elimination, it seems like we're going to be adding capacitance. So let's mathematically check that out. So we're going to have the magnitude of the voltage squared divided by the conjugate of negative 1 over J omega C. So right now we have 1 over negative J, which is going to wind up looking like negative J omega C times the magnitude of the voltage squared. So we have a complex number, which is what we're looking for, and it has to be negative, which is also what we're looking for, because we want Q to get smaller. So in order to perform power factor correction for an inductive load, which is what the overwhelming majority of industrial loads are going to be, we're going to need to add some capacitance to our system. Okay. So power factor correction relies on us adding some capacitance. So effectively what we're doing, let me do it in this light pink color, is we have some complex power that is being supplied by our capacitance. We add it to our old power factor and we get, or excuse me, we add it to our old complex power and we get our new complex power. Okay. So mathematically, we can describe this as follows, okay? So we know that S old is equal to P old plus JQ old in rectangular format, or the magnitude of S old with an angle of theta old in polar format. Okay. S new is simply P old plus JQ new, right? We hold our average power to be constant. We're only changing the reactive power. So this is going to look like S new with an angle of theta new. And we also know that S new is equal to S old plus S cap, where S cap is the complex power supplied by our capacitance. From this, we can see that S cap is simply S new minus S old, or P old plus JQ new minus P old plus JQ old. The P olds wind up canceling each other out, and we're just left with J Q new minus Q old. I want to point something out here. This will always be a negative number, because the whole point is to make Q smaller, okay? We know that capacitors, like we see right here, complex power absorbed by a capacitor is always going to be negative. So this is simply J Q cap. All right. So how are we going to relate? Actually, let me talk about what we have here, right? So we know that the complex power that is being provided by our capacitor is related to our old complex power and our new complex power. And therefore it is related to our old power factor angle and our new power factor angle, right? So we have some current power factor that we're operating at, and we have some target power factor that we're trying to operate at. We can figure out what those angles are and figure out the amount of VARs that we need in order to change that complex power, okay? Now what we're going to do is relate this to figuring out what value of capacitor is needed. Because as you guys go out and do work, working on projects and all that kind of stuff, it's not going to be how many VARs, it's which item do I buy to make this system work, right? So we have one mathematical, let me do it in a different color, expression for the complex power absorbed by a capacitor. We have another expression here for the complex power absorbed by a capacitor. So we're just going to set those things equal to each other and solve for C. That's what's going to tell us what size capacitor we need based on the parameters of the system. right? So we have JQ cap is equal to negative J omega C times the magnitude of the voltage drop across our capacitor squared. We can get rid of the J's on both sides, right? Since we're solving for C, let's put C on this side. So we're going to have to simply divide Q cap by omega times the magnitude of our voltage squared, right? We can use other identities. I'm not going to make you guys go through the derivation of this. This is mathematically the exact same thing as P old times the tangent of theta old minus the tangent of theta new divided by omega times the voltage drop across our capacitor squared. Okay. So that we can directly relate our power factors, current power factor, PF old, and target power factor, PF new, into an equation so that we know what size capacitor to get. Okay. So let's work a couple of examples here. All right. Let's start with something pretty simple and straightforward. Let's say that I have a voltage source, 400 angle 0 degrees volts RMS at an operating frequency of F is equal to 50 hertz. So this is a pretty standard industrial voltage in Europe. And we are supplying power to a motor. Right. Our motor absorbs 1 kilowatt of power at a power factor of 0.8 lagging. And we want to know what value of capacitor is needed to increase the power factor at which the motor is absorbing power from 0.8 lagging to 0.975 leading. Okay. Now, realistically here, your utility doesn't care whether you're operating at a power factor of 97.5% leading or lagging. We'd actually be overcorrecting this thing because we would be overshooting a unity power factor, which is the ideal case. But I want to point out a couple of things with the math that happens when you have a leading power factor. So this is why I'm doing this. For all practical purposes, you would probably actually design your system to operate at 97.5% lagging because it's going to use a smaller capacitor and therefore it's going to be cheaper. And when you guys go out into industry, cost is going to be one of the biggest things that you have to pay attention to. Okay. All right. So effectively, what's happening is we have a load that's drawing some amount of complex power. We want to figure out what value capacitor makes it draw less complex power so that it operates more efficiently. Okay. So if we look at our equation here, let me just write it down here. We can say that C is equal to P old times the tangent of theta old minus the tangent of theta new divided by omega times the magnitude of the voltage drop across the capacitor squared, right? So we need what looks to me like 5 pieces of information. We need P old, we need P new, or excuse me, we need P old, we need theta old, we need theta new, we know omega, or we need omega, and we need the voltage drop across the capacitor. So which of those things do we already have? So we don't have theta old specifically, but we can get it pretty easily, right? So let's do that. So how are we going to find theta old based on the information that I've given you? I'm sorry, I couldn't hear what somebody mentioned. Absolutely, it's 100% correct. So we are given PF old, right? 0.8, and we can use that to find theta old. Let's scroll up here just a smidge. Let's look at this relationship, right? So Avery is 100% right. PF old is equal to the cosine of theta old. So if we're needing to find theta old, then we do the arc cosine of the power factor, right? So in this case, that's going to be the inverse cosine of 0.8 is going to be equal to what? (36.87 degrees). Absolutely. Let me ask you guys a question. Is this angle positive or negative? Because the inverse cosine operation on your calculator will only give you a positive answer. Okay. Since it's lagging, it'll be positive, right? So if we look at our notes from last class meeting, whenever our power factor angle is positive, we operate at a lagging power factor. Whenever our power factor angle is negative, we will be operating at a leading power factor. So this angle should be positive. We can do something similar here to figure out what theta new is, right? Because we know what our new power factor is. So theta new is going to be the inverse cosine of PF new, which is going to be the inverse cosine of 0.975, which is so 12.836 degrees. And then you absolutely correctly denoted that it should be a negative number because we're operating at a leading power factor. So typically speaking, I usually just put a negative sign out front here to remind myself that we're operating at a leading power factor, okay? So the expectation is if we're operating a lagging power factor, our angle should be positive. If we're operating at a leading power factor, our angle should be negative. Because our calculator will only give us a positive angle, we have to manually put that negative angle in. Okay, so I just want to be clear about that. All right, so we found theta old and we found theta new. So we are 2/5 of the way done. What about the other pieces of information? So I think I gave you 2 of them. We have the voltage, absolutely right. That's just 400 volts RMS. Right. So because we're dealing with the magnitude of the voltage squared, we're going to throw away any phase angle that we have. We only want that front part, right? What other piece of information did I give you guys directly? So I would consider the frequency indirect. I did give you the linear frequency F. How do we get the angular frequency omega that we need? 2 pi times F, absolutely right. So omega is 2 pi F. So that's going to be 100 pi radians per second. All right, so what's that leave us with? Field. How are we going to get that? I'm gonna give you a hint. I gave it to you. Yes. Yes, but we don't have S. It's just the 1 kilowatt. Absolutely right, because kilowatt tells us that that's average power. Don't need to do any work for it whatsoever. I literally gave it to you. You just have to be able to recognize what was given to you by looking at the units of the power there. So P old simply 1 kilowatt. All right. So let's just throw all these numbers into our calculator here. So I'm going to say 1,000. That's 1 kilowatt times the tangent of 36.87 minus the tangent of negative 12.836. All of that is divided by 100. We got to figure out where the pi button is on this calculator. There we go. Times 400 squared. So plugging in our numbers, I get 1.945 times 10 to the minus 5 farads, or 19.454 microfarads. Congratulations, you guys have just figured out how to correct the power factor of a motor by using a capacitor. Now, I can make this slightly harder by including some line impedance, right? So effectively what I'm saying here is the wire that we use to connect our voltage source to our motor is also going to have some amount of impedance. And so it is also going to play some role in a practical system, right? So let's look at something a little more difficult. So let's say that I have some voltage source VS here. And to make things slightly harder, I don't know what this voltage is. I have a 0.05 ohm resistance in series with a 0.2 ohm inductance. So this represents the impedance of my transmission line that is connecting my voltage source to my loads. And I'm going to have a composite load here. So that just means I'm going to have a couple of loads connected in parallel. I'm going to call this voltage VL. So the voltage that's being applied to my loads is 240 angle 0 degrees volts RMS at a frequency of 60 hertz. So this would be something like we would see if we were trying to connect maybe our dryer and our stove in parallel here in the United States. Load number 1 absorbs 20 kilowatts at a power factor of 0.7 lagging. Load number 2 draws 12 kVA at a power factor of 0.9 leading. And we want to determine the value of the capacitor C that would make the source VS supply power at a power factor of 0.95 lagging. And just to be clear here, we're going to apply our power factor correction capacitor in parallel with our voltage source. Okay. So, not going to lie to you, this is a significant jump up in complexity from the previous problem, okay? It's nothing insurmountable. We're going to use pretty much the exact same relationships, but we're going to have to do a little bit more thinking because we actually have a slightly more complicated circuit and maybe a little less information than we had the last time. So our goal here is to figure out how to correct the power factor of our voltage source on the left-hand side, which means we're going to need to know the voltage drop across our voltage source, which wasn't given to us. We're going to need to know the power factor at which our voltage source used to operate, which wasn't given to us. The power factor that our voltage source is going to operate at after power factor correction, which was given to us, so we can figure out theta nu from that. We need to know omega, which was effectively given to us because we have our linear frequency there, and we're going to need to know the old power factor, the old average power that our voltage source is supplying, right? So there's lots of pieces of information that we're going to need here. Anybody have any thoughts on anything? So I'm going to say something here, hopefully not too mind-blowing, but I would argue pretty strongly that whatever complex power is being supplied by the source has to be equal to the complex power that's being absorbed by those loads, as well as whatever complex power is absorbed by our wire, right? So effectively, what I am suggesting is that, let me do this in a different color. The complex power of our voltage source is going to equal to the complex power of our wire plus the complex power absorbed by load 1 plus the complex power absorbed by load 2. Anybody have a problem with that? Energy in equals energy out. Not at all. Powers are just powers. Yep. So no, you can just add them together. It's a principle called Kelvin's theorem, but it's also simply the law of conservation of energy. All right, so we have three things that we need to figure out then. Complex power absorbed by our wire, complex power absorbed by load 1, complex power absorbed by load 2. I would argue that figuring out the complex power absorbed by load 1 and the complex power absorbed by load 2 are much easier to figure out than the wire. In fact, I believe that we have to know those two quantities before we can figure out what's going on with the wire. Okay. So how am I going to figure out the complex power absorbed by load 1? What do I know about load 1? Power factor and the average power. Absolutely right. So if I know the average power and I know the power factor, that's literally all I need to know to figure out the complex power. And that's just going to use those relationships. Let me scroll way back up here. These guys, right? So I can manipulate this expression and I can say that the magnitude of my power factor, or excuse me, the magnitude of my complex power, S old, is just going to be P old divided by PF old. And the angle theta is just the inverse cosine of our power factor. That gives me both parts of my complex power, both the magnitude and the angle, right? So for S load 1 here, we are going to have P load 1 over PF load 1 with an angle of inverse cosine PF load 1. Let's throw some numbers at this. So that was 20 kilowatts over 0.7 with an angle of the inverse cosine of 0.7. Which I get to be 28.571 with an angle of 45.573 degrees kVA. Is that angle supposed to be positive or negative? Positive. Why? Because it's lagging. I'm going to burn that into you guys' brain. Okay. So anybody have any questions, comments, or concerns about where all this information came from? We're going to manipulate that little power factor equation a hell of a lot today. Okay. So we're all in relative agreement that S load 1 is this. Now let's talk about figuring out S load 2. So I'm going to scroll up here. What do we know about load number 2? So we definitely have the power factor. I've heard some people say that we have the average power, which I disagree with. Preston, what do we have? Yeah, that is the apparent power. Yep, all we need to do is find the angle. 100% right. Right? Because the units here were given to us in kilovolt amperes, we know that this was the apparent power. The magnitude of the complex power is the apparent power, right? So we don't need to divide by our power factor or anything here. We're actually already given the thing that we're looking for. So this is just going to be the apparent power of load 2 with an angle of the inverse power factor of load 2. And because the power factor of load 2 was leading, I'm going to put a negative sign out front to remind me that my angle is supposed to come back as a negative quantity. So this is going to look like 12 kVA negative inverse cosine of 0.9. Actually, before I do that, I'm going to store my answer as A. So now we're going to have 12 angle negative inverse cosine 0.9, store it as B. So that's going to be 12 angle negative 25.842 degrees. So now we come to needing to figure out what the power, complex power absorbed by our wire is. Okay. We're not given anything but the impedance, which means that we're going to need to know the voltage drop across the wire, which we don't know, and the current flowing through the wire, which we also don't know. How are we going to figure out those things? So I'm going to call this current. I wire. And this voltage drop V wire, right? If I know one, I can get the other, just using good old Ohm's law. Okay. So I would argue here that figuring out the current flowing through the wire is significantly easier than figuring out the voltage drop across the wire. The reason why I say that is because we don't know what our source voltage is, right? If we knew what our source voltage was, the voltage drop across the wire would just be our source voltage minus our load voltage, easy peasy, using Kirchhoff's voltage law. Instead, because we don't know what Vs is, we're going to have to figure out what our current is. And we can figure out what our current is by applying Kirchhoff's current law to the system, right? So I have some current here. I'm just going to call it I1. And I have some current flowing through load 2 that I'm going to call I2. And the current flowing through my wire is just the sum of the current flowing through load 1 plus the current flowing through load 2. Anybody have a problem with that? So current flowing in to that node equals current flowing out. Straight application of Kirchhoff's current law, nothing wild or particularly fancy there. How are we going to figure out I1 and I2? Exactly right. We have the power and the voltage, and we know complex power. So let's write this down here, right? So S load 1 is just going to be VL times what I have as I1 conjugate, and a similar thing for S load 2, right? So we're going to rearrange this thing. Okay. So I could say that I1 conjugate is equal to S load 1 divided by VL. And to get rid of the conjugate on this side, I'll just perform the conjugate on the other side, because the conjugate of the conjugate on the left-hand side is just changing the sign on the imaginary part twice. Okay. So our current I1 is going to be 28.571 angle negative 45.573 degrees kilovolt amperes. divided by the conjugate of our voltage, where VL was 240 angle 0. And I know this is silly. Volts RMS. I'm putting -0 there just to remind myself that when I take the conjugate of a fraction, I need to conjugate both the numerator and the denominator. Or you could literally just tell your calculator, do the fraction and then take the conjugate of the result. Either way works. So because I already have this bit here stored in my calculator as X, I'm going to do the conjugate of, excuse me, A, because I'm using the Casio calculator. Conjugate of A over 240 angle 0. And this comes out as 0.119 angle -45.573 degrees. What are my units here? It's going to be kiloamps, because I have kilovolt amperes divided by volts is going to give me kiloamps, right? So kiloamps RMS. I can do effectively the exact same thing to figure out what I2 is. That's going to be the conjugate of S load 2 over VL, which is going to look like 12 angle positive 25.842 degrees kilovolt ampere divided by that same 240 angle -0 degrees volts RMS. I get 0.05 angle positive 25.842 degrees kiloamps RMS. And from this, I wire is just I1 plus I2. So 0.119 angle -45.573 plus 0.05 angle 25.842 gives me 0.143 angle -26.221 degrees kiloamps RMS. The voltage drop across my wire is then simply I wire times Z wire. Z wire is 0.05 plus 0.2 I. Giving me 0.0295 angle 49.743 degrees kilovolts RMS. And I'm going to go ahead and multiply that by a factor of 1,000 to give me the answer in volts. right? So I know the voltage drop across my transmission line or my wire. I know the current flowing through my transmission line or wire. How do I get the complex power? V times the conjugate of I, right? Just our basic bare bones equation. S wire is V wire times I wire conjugate. So that's going to be 29.484 angle 49.743 degrees volts times 0.143 angle negative 26.221 degrees kiloamps RMS. Gives me 4.216 angle 23.522 degrees kilovolt amperes. I did not. Thank you for that. Yeah, I was wondering why my angle was wrong from what my notes were. So thank you very much for that. I did not do that, so let me do that right now. Or actually, I'll just write the damn number. It's just those two angles added together. So 49.743 and 26.221 is going to be something in the ballpark of 75.964 degrees. This doesn't add up directly because I've got a little rounding error, but it'll be that or something close to that. Okay. So thank you very much for pointing that out. I forgot to do the conjugate of the current, which means that angle was wrong, which was going to mess everything else up. So cannot iterate enough how much bookkeeping this complex math entails. All right. So from here, I know this part, I know this part, I know this part. I can simply add them all together. And that's going to tell me the complex power of my total system connected to my voltage source. So SVS is S load 1 plus S load 2 plus S wire, which I get to be 37.201 with an angle of 31.192 degrees kVA. Up close to that when you add those three numbers together. So after pretty large amount of work, we can now figure out two of the three things that we need, right? From this, we can figure out P old and we can figure out theta old, right? Well, actually, theta old is right there. We don't really need to figure it out, okay? So theta old is 31.192 degrees. How do we get P old? If I express that complex power in rectangular form, that's going to have P old and Q old, right? So in rectangular form, that's going to be 31.823 plus J 19.267 kilovolt amperes. And so from that, P old is 31.823 kilowatts. Right, so the real part of the complex power is simply the average power. So we have theta old and P old, so that's great. What we're missing now, theta new, the voltage drop across the capacitor, and our frequency. So which one of those three pieces of information you guys want to tackle next? The voltage, okay? So we're going to figure out VS. We know V wire, we know VL. How do we do it? Yeah, just add them. VS is just going to be V wire plus VL. 100% right. That's what Kirchhoff's voltage law tells us. So V wire was, get it here, 29.484, angle 49 and some change, so 29.484, angle. Where the hell did it go? 49.743. VL was just 240 angle 0 degrees. So if we add those two numbers together, 29.484 angle 49.743 plus 240 gives me 260. Go away. 0.028. Angle 4.964 degrees. Volts RMS. So the magnitude of the voltage that we need to plug into our capacitor equation is just that 260.028 volts RMS. All right. Now we're missing theta nu and omega. The two easiest things to figure out. Let's start with omega. How do we find omega? Rolling up here, we have our linear frequency, 2 pi times that. Now we need theta nu. What's theta nu related to? Right. Our new power factor is right here, 0.95 lagging. So theta nu is simply going to be the inverse cosine of 0.95. Positive 18.195 degrees. All right. And now we can figure out C. C is P old times the tangent theta old minus the tangent of theta nu divided by omega times the magnitude of our voltage squared. So that is 31,823 times the tangent of theta old, 31.192 minus the tangent of theta nu, 18.195 divided by omega was 120 pi times 260.028 squared. 3.455 times 10 to the minus 4 farads. So that's about 345 microfarad capacity. So if you were, if you were able to follow all of that, doing great. This is way harder than anything I'll ever give you on an exam. It is pretty much as hard as the hardest homework problem I'm going to give you. All right, so time for the in-class assignment, which I'll distribute right now. What you see on this in-class assignment is much more in line with what you should expect on your exam. And speaking of your exam, I believe it's that